This lecture is all about the analysis of variance, or the ANOVA. And if you think about the term analysis of variance, it has two parts, analysis and variance. Well, the analysis is just breaking things down into components. And then the variance, you're separating the variance in the dependent variable due to the independent variable from the variance due to just chance or random sampling error. And variance, remember, is just a measure of the differences in scores. So we're breaking down all of those differences among scores to see how much of those differences are due to the independent variable and then how much of those differences are due to everything else. And one of the great things about ANOVA, which we'll talk about here in a little bit, is that the ANOVA can be used much like when you have a t-test for independent samples. But you can use an ANOVA when you have two or more levels of the independent variable. So more than just two groups. So a summary of the topics in this lecture. I will show you guys the differences between t-tests, which we've been talking about a lot lately, and the ANOVA. And then I will show you the F distribution, which is the table for the sampling distribution that we're going to be using for the ANOVA. So when we calculate the F statistic in step 3, that's the statistic that we are calculating for the analysis of variance, F statistic. Moving on from T and going into F for ANOVA. Then I will break down the difference between and within groups differences, or between and within groups variance, which is used to calculate the F statistic. Then I'll show you all the statistical notation for ANOVA and how to compute that F statistic. Then I'll show you how to calculate effect size and post hoc analyses in ANOVA. And then I'll show you how to understand the relationship between all of the components of the F statistic calculation. So we're going to be putting all of these calculations that lead up to the calculation of F in something that's called a source table. And I'll show you how all of the values in the source table are related. And then I'll show you two examples of an ANOVA hypothesis test where we calculate effect size and we do that post hoc analysis, which is called Tukey's HSD. So just a couple quick things about how t-tests compare to the analysis of variance. So for the t single sample, remember we were testing a hypothesis about a single sample mean compared to a single population mean. And the point of it was we were doing something to a sample and seeing if that effect was significant so that we'd be confident that we would see similar results in the population as well. Well then, in the independent measures test, we were testing a hypothesis about the difference between two population means by using two different samples and seeing if the results in our analysis were significant with those two samples to then be confident that whatever we observed in those two samples would also be observed in these two hypothetical populations. The population if everybody received whatever the group received as far as the independent variable goes. Well now, like I said earlier, we're moving on to ANOVA, so calculating the F statistic in step 3 of the hypothesis test. And ANOVA allows you to test the hypothesis about the difference between two or more population means using the samples. So you can have as many different levels of the independent variable as you like and do an analysis of variance and have a single analysis that tells you if there's a significant difference somewhere. So it's important to note that for our purposes, we're only going to be doing a one-way ANOVA, meaning that we only have one factor or one independent variable. So the word factor is synonymous with the term independent variable. So we just have one factor in our one-way ANOVA, and we can have many levels, as many levels as you want of that one factor. So let me give you a couple of examples of a one-way ANOVA scenario. So maybe you want to compare benevolent sexism perceptions across sexual orientations. So in this example, benevolent sexism would be your dependent variable, and then sexual orientations would be your quasi-independent variable. I call that quasi-independent variable because we're not manipulating someone's sexual orientation. We can't say, oh, well, you're going to be in the straight group and you're going to be in the gay group. It doesn't work out that way. So it's a quasi-independent variable. But we think that sexual orientation is going to predict benevolent sexism perceptions. So in this case, we have a single factor, a single quasi-independent variable, sexual orientation. But there's multiple levels of that independent variable. So you could measure people to see if they're heterosexual, gay males, lesbians, and bisexual. So you'd have 4 different levels of sexual orientation. Another example of a one-way analysis of variance situation that you could have. And we'll actually do an example with this scenario. So let's say that we want to compare the effectiveness of pain relief drugs on pain intensity. Well, pain relief drugs would be our factor, our independent variable, and pain intensity would be the dependent variable. And we could have as many levels of this as we want, but let's just say, for example's sake, that we have 3 different groups. One group gets morphine, another group gets fentanyl, and another group gets a sugar pill that's a placebo. Well, in that case, we have 3 levels of that single independent variable, or 3 different types of drug, or no drug at all. So it's also important for you to realize, even though we're not going to cover this in this class, the analysis of variance can be used to examine the impact of multiple factors on a dependent variable. So again, we're only going to look at one independent variable, but the analysis of variance is a really powerful tool because not only can you look at multiple levels of an independent variable, but you can look at multiple independent variables synonymously at the same time to see how they impact the dependent variable independently and how they interact to have an impact on the dependent variable. So for example, let's say that you wanted to examine the effectiveness of pain relief drugs between males and females. So you could see if the different drugs have a different impact on pain, and you could see if the effectiveness of the drug depends on the sex of the person. You could also have an example where you want to look at the impact of commercial volume on persuasion. So persuasion would be our dependent variable, commercial volume would be our independent variable, and let's say that we think that that's going to differ based on, again, being male or female. Well, in that case, you have 2 factors. You have 2 independent variables. You have one that's volume. Let's say that you look at soft, medium, and loud volume. So you have 3 levels of that independent variable. Then you have sex, which is your quasi-independent variable. You have 2 levels of that, males and females. So those are powerful tools because not only could, in that example, you could see, does commercial volume have an impact on persuasion? Does sex have an impact on persuasion? So are females or males more likely to be persuaded by commercials? And then, does the commercial volume's effectiveness on persuasion depend on your sex? So that's more complicated than what we're going to get into in this class, but if you're interested, you can read the chapter about that in your textbook. One last thing, just because I think ANOVAs are great, and I'm sad that we're not covering all the ways that ANOVA can be used, you can also look at an independent variable and measure it over time. So you can kind of compare you can kind of take an ANOVA with multiple levels of an independent variable and combine it with like the t-test for repeated measures. And you can mix that, and that's a mixed design ANOVA. That goes way beyond the scope of this class, but it's a really nifty thing that you can do with analysis of variance. So both the t-statistic and the F-statistic for the ANOVA compare the actual sample mean differences to the differences expected by chance if the independent variable has no effect, or if the null is true, saying nothing's happening. But it's important to note that the calculations differ for F versus T. So in an ANOVA, chances are you're going to have more than 2 groups. So you can do an ANOVA with just 2 groups, or you could do a t-independent samples test. Either one is fine when you only have 2 groups. But when you have more than 2 groups, you want to do an ANOVA. And when you have more than 2 groups, it's impossible to calculate a mean difference. You can't find the mean difference between more than 2 groups. So the variance is used to represent the size of the mean differences between 2 or more samples. Variance is just another measure of differences that can be used with more than 2 groups and still be an accurate reflection of something, of the differences. So if you look at the calculation for T, which is right here, you'll see that T is the observed mean difference between 2 sample means divided by that standard error. So we take M1 minus M2, and we compare that to what we would expect to see the difference if the independent variable has no effect. Now for F, remember, we can't look at mean differences. So we're looking at the overall differences between treatment conditions, which is the variance between treatment conditions, and dividing that by differences within each treatment condition, or the variance within each treatment condition. And I'll get into what is between and within groups variance here in a minute. But just keep in mind that we've got, let's just say, for example, 3 different groups, and we're measuring their dependent variable, and we know that these groups are different based on the level of the independent variable that they received. Well, not only are you going to be looking at the differences between each group, so the differences in scores for person in group 1 versus group 2 versus group 3, but you'll also want to look at the differences within each group, so within a single group that received the same level of the independent variable, because that'll give you a measure of chance differences. Because think about it, they got the same level of the independent variable, so any differences among their scores can't be due to receiving a different level of the independent variable because they got the same level of the independent variable. So that's why it's important to not only look at between group differences, but also within. Now, if you have a situation where there's no differences between groups that's due to the independent variable, then your F is going to be 1 because the differences between treatment conditions are the overall differences because of the variability due to the independent variable and the variability due to just random differences. And then the differences within are just the variability due to random differences. So if the variability due to the independent variable is none, 0, then you end up with an F statistic that's the variability due to random differences divided by the same variability due to random differences, and any number divided by itself gives you 1. Now, if you have a situation where there's no difference between each group, so if you add up the X values for each group and take the mean, so divide it by how many scores you have, and you find that there's really no difference, then you would have an F statistic that is 0. Because if you have no differences between groups, well, 0 divided by anything is going to be 0. So that being said, when you think about the F distribution, it's no longer that nice normal curve. So remember, the F distribution represents the sampling distribution, or all of the possible values for F if the null is true. Or in other words, all the possible values of F if there is no difference based on the independent variable. And this sampling distribution is based on the sample size and the number of levels of the independent variable, which you'll see shortly when we do step 2 of the hypothesis test, finding the critical value. So first thing, the F distribution is based on variability, and variability is never negative. You can never have a negative spread of scores. Also, if you think about it, remember I said if there's no difference between groups, then your F statistic will be 0. So that is the bare minimum. That's the lowest you can have. There's just no difference whatsoever. So that would be the lowest end of the distribution. There are no negative values in the F distribution. And then remember, the sampling distribution represents all possible values for F if the null is true and there is no difference due to the independent variable. So according to the null, most of the differences will be just due to within groups differences. So just due to random error, random chance differences, not due to the independent variable. Remember, because this represents the null hypothesis. And remember, I said that if you don't have any variability between groups that's due to the independent variable, then your F value will be 1. So according to the null, most of the F values that you calculate if the null is true would be 1. And then as you start to get out into more extreme F scores, where we're saying that there is quite a bit more difference due to the independent variable than just differences due to chance, then you're going to get larger F values, and these are where you'll be looking for your critical regions. So for the F distribution, there is no one or two-tailed test. It's a positively skewed distribution, and there's only one tail that we care about, the tail that's on the extreme end, saying that we have a higher F value, we have more extreme differences between groups who do vary with respect to the independent variable, and that those differences exceed the differences within the groups who do not vary with respect to the independent variable. Now let's break down the between and within group differences. And this is really important because this is all about what's being calculated in your F statistic for your ANOVA. So before we discuss the calculation of F, I want to talk about what contributes to these differences between and differences within groups. So the between levels or between groups or between conditions, levels, conditions, groups, all synonymous with each other. So the between levels variability can be due to three things. It can be due to the treatment effect, or the independent variable, and this is what we hope the differences are due to. So we're hoping that the differences in the dependent variable among the different levels of the independent variable are due to what we manipulated, the independent variable. But those differences between groups can also be due to individual differences. So differences in, I don't know, pain tolerance or initial pain levels if we're looking at the effect of pain medication on pain, or maybe differences in intelligence or motivation if we're looking for the effect of like on-the-job training on job knowledge. So just individual differences. Now these individual differences can be minimized by randomization. So not only do you want to take a random sample, but you want to randomly assign your sample to the different groups. So you're hoping that those individual differences kind of weed out. So if you have a self or a convenience selection where you allow people to choose what group they're in, or you don't have a random sample to begin with and you have all volunteers participating in the study, well, that's going to increase your sampling error, and it's going to result in systematic sampling error that can't be statistically controlled for. We can only statistically control for that random error difference within each group, but not differences due to poor methodology. So when you think about individual differences and the importance of randomization, let's say, for example, in that pain study, participants in the morphine group were recruited from a back pain clinic, and participants for the fentanyl group were recruited from an arthritis clinic. And in that situation, there's already differences in pain levels prior to any manipulation of the drug. And they're probably going to have different reactions to the drug because they have a different type of pain. So that would be that systematic sampling error that you want to avoid through randomization. Now, the third source of between groups differences is experimental error. So this is when the experimenter unintentionally treats groups differently or just has poor methodology. So back to the pain example. Let's say that the experimenter, who administers the medication and guides participants through tasks and collects data, that person should not know which medication is being administered and which group participants belong to. Because think about it, if the experimenter knows, then that experimenter may treat the groups differently, which can result in misleading differences in pain. So I've used this example before. Let's say that we're having these people perform some physical activity and we're seeing how long they can perform it before the pain is too great. Well, if the experimenter knows who's getting a sugar pill, he may go easy on them because he doesn't want to inflict pain on them when he knows that they aren't getting any of the drug. So he may feel guilty. Also, you don't want the participants to know which group that they belong to, especially the control group, because they may be resentful and may try to contaminate your results. So if the participant knows, then they may have some psychosomatic symptoms because they either know that they're getting a sugar pill or they know they're getting a drug, so a placebo effect, or they may just be resentful for being in the control group. So you may risk purposeful contamination of results, which is never a good thing. So if you've ever heard of a double-blind study, that means that not only does the experimenter not know which group is getting which drug, but the participants don't know either. And then there's a third party who collects the data and knows who's getting what level of the independent variable and can do the analysis later. But that person who's aware of what groups or what people in what groups doesn't interact with the participants at all. Now, when you look at within groups differences, those differences can only be due to the individual differences I talked about earlier, or the experimental error or experimenter error, which just means that they unintentionally treated individual participants within the group differently. So the F-statistic provides a way to isolate the treatment effect, this number 1 here, by comparing it to the error variance. So the variance due to individual differences and experimental error. So the numerator of the F-statistic includes treatment effect, individual differences, and experimental error. The denominator only includes individual differences and experimental error, so we can isolate the effect of the independent variable on the dependent variable that's being measured. So before I go into some examples of doing calculations with the analysis of variance and hypothesis testing and all that fun stuff, I want to break down some of the statistical notation and the actual formulas that you'll be using in the analysis of variance. So the first thing that you want to know about is this thing called the factor. And the factor is just the word for the independent or quasi-independent variable. Remember, it's called an independent variable if it's something that's manipulated. It's called a quasi-independent variable if it's something that forms the basis of the different groups, but it's not something that's actually manipulated. And remember, the independent variable or quasi-independent variable is the predictor variable in the study. Then levels is just the individual conditions or groups that differ with respect to the independent variable. So K just tells you the number of levels. So if you think about like the benevolent sexism example where we thought that sexual orientation would predict benevolent sexism. Well, sexual orientation is your factor, and there were 4 levels of that: bisexual, gay male, lesbian, heterosexual. And so K would equal 4 in that case. Then uppercase N is the entire sample size across all levels in the study. So how many people participated in the study? Then lowercase n is the sample size for just one level or just one group or one condition. So you think about the relationship between lowercase n and uppercase n. The sum of all the lowercase n's will give you the uppercase n. The sum of all these sample sizes for every level will tell you how many people participated in the entire study. Because just like the t-independent measures test, you are not going to have any person who's in multiple groups. Every person only receives one level of the independent variable. Then T is the total or the sum of X for a single level. T stands for total. And then G is the grand total for all the scores across all the levels. So similarly to N, if you think about the relationship between G and T, the sum of all the T's will give you G, because you're adding all the scores for all the levels to get G. So in looking at the calculations for the ANOVA, it may look intimidating, but it's not. And when you do your final answers, I would really appreciate that you put them in this source table, because it keeps you organized and it helps me figure out all the calculations that you did if you need to get partial credit. So the only calculation in ANOVA that's difficult is the sum of squares total. I will be giving you the sum of squares for each group. So the sum of squares within, you'll just add those sum of squares that's given to you. And then for sum of squares between, you can find the sum of squares total and subtract the sum of squares within, and you end up with the sum of squares between. Or you can use this formula up here to check your work to make sure that this is the same as this. But this formula is kind of difficult to use. So just to break down this formula, if you opt to do that, T, remember, represents the sum for one level. So the sum of T squared divided by N, that is like saying if we have 3 groups, we're going to have 3 of these, add them together, minus the G grand total squared divided by N. So you would have the sum of X for group 1 squared divided by 2, or sorry, divided by the sample size, plus the sum of X for group 2 squared divided by the sample size for group 2. Let's say you had 3 groups, so the sum of X for group 3 squared divided by the sample size for group 3. Add all those together, and then you would subtract the grand total squared divided by the sample size for the entire study. I'm not going to even demonstrate this because it's so easy to just calculate sum of squares total, add up all the sum of squares for each treatment, those will be given to you, and then find the difference for sum of squares between. Now, sum of squares total should look pretty familiar to you. This is essentially the same thing as the sum of squares formula that we've been using for the T independent samples and the T single samples, and just the sum of squares for a single sample in general. So it's the sum of all the scores squared minus the sum of all the scores, that thing squared, divided by the sample size, in this case for the entire study. So moving on to the degrees of freedom. So the degrees of freedom between is equal to K minus 1, or the number of levels minus 1. So in that benevolent sexism example, if you had 4 different sexual orientations, 4 minus 1 would be 3. So you're thinking about the number of treatment totals minus 1. And degrees of freedom always reflects the number of pieces of information being used to calculate something minus 1. So number of treatment totals is the information that's used to calculate the sum of squares between, and you take that minus 1 to get your degrees of freedom. Sum of squares within, each sum of squares value that we are using to calculate the within portion of the variability, each one of those sum of squares measures variability for n scores in the treatment condition or the group. So each treatment or each level has a degrees of freedom of n minus 1, so you just add the degrees of freedom for each treatment. So if you had 3 groups, for example, you could take n1 minus 1 plus n2 minus 1 plus n3 minus 1 to get the degrees of freedom, or you could simply take all of those n's added together, so uppercase N, subtract it from 3, or in that case that would be k. So it's kind of like the independent samples t-test, where you could, take degrees of freedom 1 plus degrees of freedom 2, or you could just take n, the sample size for the entire study, minus 2, and in that case 2 was the only number of groups that we could have for the independent measures test. Then finally, degrees of freedom total is really just meant to help you check your work here. It's the sample size for the entire study minus 1, and you should find that degrees of freedom for between plus degrees of freedom within equals degrees of freedom total. Then when we move on to the mean squared is equal to variance. So if you think about the calculation for variance that we've been using all along, it's the sum of squares divided by the degrees of freedom. So kind of like an average of the total differences in the squared version of those total differences. So when you think about the calculations, you find sum of squares total, you add up all the sum of squares for each group for sum of squares within, take the difference here, then you do these simple calculations for degrees of freedom, and then you just divide degrees or sum of squares between by degrees of freedom between, boom, mean squares between, your variance between. Then sum of squares within divided by degrees of freedom within, boom, you've got your mean squared within, or your variance within. So your variance due to the independent variable and error differences, or just random differences, divided by, here for your F statistic, your variance that's just due to error. So you calculate degrees of freedom and sum of squares, then you take sum of squares divided by degrees of freedom for both between and within, and then for F, you just take mean squares between, divide by mean squares within. So all these variables are related to each other, and doing this will help you see how you can just use the source table for your calculations and it makes sense. So before we move on to doing an example of a hypothesis test for ANOVA, I want to show you some calculations that are really important to consider if your ANOVA result is significant. So the first thing is effect size. So, significance just says, yeah, we know that there's some difference. There's a significant difference due to the independent variable, but how much of those differences in the dependent variable can be attributed to the independent variable? Well, that's what effect size is all about. And this is called eta squared, and it's pretty much akin to r squared. The interpretation's still the same. It still tells you the proportion of variability in scores on the dependent variable that can be accounted for by the treatment condition, or the independent variable. But the calculation is a little bit different. You can also compare what you get for eta squared to the criteria for r squared as far as small, medium, and large effect that we've been using all semester. So to find eta squared, you just take the sum of squares between, divide by the sum of squares total, and you've got your measure of effect size. Now, one thing about the ANOVA is that if you get a significant result, that only tells you that there's at least one pair of groups that are significantly different. Or at least, one group that is significantly different from one other group. But it doesn't tell you which groups are significantly different. Now, you may have already wondered, why don't you just do a bunch of t-tests for independent samples? Like if you had 3 groups, you could just do a t-test comparing group 1 to group 2, a t-test comparing group 1 to group 3, and a t-test comparing group 2 to group 3. Well, you don't want to do that because every hypothesis test that you do has a certain probability of type 1 error. Well, if you do a bunch of t-tests, you're inflating that risk of type 1 error with each subsequent test that you do. But if you do an ANOVA, it's a single hypothesis test with a single fixed probability of type 1 error, which if you remember equals your alpha level, and you're not inflating that risk of type 1 error with a bunch of hypothesis tests. So the ANOVA is great because you just have a fixed type 1 error. You don't have a bunch of hypothesis tests with type 1 error accumulating over time, but it leaves you with a problem where you just know there's a significant difference if you get a significant finding, but you don't know which groups are significantly different. And in most cases, you do want to know which groups are significantly different. For example, in the pain study, if you get a significant result, you want to know which drug is the most effective. So you would want to do a post hoc analysis, and one of those post hoc analysis is Tukey's HSD. HSD stands for honestly significant difference. And what this tells you is the mean difference necessary between two groups to be considered significant. So you'll calculate Q times the square root of the mean squares within divided by n. And that'll tell you the mean difference that needs to occur between two groups to be a significant difference. So once you calculate this, and I'll break down how to calculate this here in a second, you'll have to take all of the mean differences between all pairs of all the means in your study, and then compare those to the value that you get here. And if you have a pairwise difference, or a difference between two means, that's equal to or greater than Tukey's HSD, then you know it's a significant difference. So Tukey's HSD is kind of like a critical value. So the way that you get this value is you find Q in a table, and I'll break down how to find Q. So you'll see the studentized range statistic table. It's B5 in the back of your book, and you'll see the little Q here, which tells you, hey, this is the Q table. So you need to know the degrees of freedom error. Well, the degrees of freedom error is referring to, in this case, the degrees of freedom within. So in the ANOVA, the degrees of freedom error refers to degrees of freedom within. So remember, the within portion of the calculation, or the denominator of the F statistic, represents the variability that's just due to error, or within groups variability. So that's why when you see degrees of freedom error, it's talking about the degrees of freedom within. And when you look at the F table and you see degrees of freedom denominator, that's also talking about the degrees of freedom within. Okay. You also need to consider the number of treatments. So how many levels do you have? And you'll find that here. And then once you locate your degrees of freedom and the number of treatments, you'll want to see which critical value you're using based on the alpha level. So the light value is alpha level of 0.05, the dark value is an alpha level of 0.01, and you can see that up here. It tells you that. So don't start looking around for a formula of how do I calculate Q? You don't calculate Q, you find it in the table and then you use that to calculate Tukey's HSD. So you'll take whatever value you find in the table, multiply it by the square root of the mean squares within, which you already calculated in step 3 of your hypothesis test, divided by the sample size for a single group. So to hand calculate Tukey's HSD, you need to have an equal sample size across all of your groups, because this just represents N for each group, not N added together. So let's say that you had 4 groups of 5 participants in each group. Well, 5 would be your N, not 20, not, the total number of participants, just the number of participants for a single group. So let's go ahead and work through an example of a hypothesis test with ANOVA, and then how to calculate effect size, and then figure out which groups are significantly different using Tukey's HSD. So let's go ahead and figure out some calculations on the example I've been talking about, where we're trying to look at the effectiveness of different pain relief drugs on pain intensity among chronic pain patients. And let's say a researcher randomly selects 15 chronic pain patients, and they all participate in the study, and he splits them up into 3 groups. So 5 get morphine, 5 receive fentanyl, and 5 are in a control group where they just get a sugar pill. Each participant is asked to only use the medication for the study over the course of the next 3 days. And then let's say after 3 days of taking the medication, they come into the lab and they provide their ratings of pain relief on a scale from 0 to 10. So in this case, we're hoping for 10s, right? We want more relief if we think that a specific drug is going to be working. So the question is, do results suggest there's a significant difference in pain relief among the three groups? And if so, what's the size of the effect and which groups are significantly different? So keep in mind here, there's no one or two-tailed test. The ANOVA only tells you there's a significant difference somewhere, but you need to do Tukey's post-hoc analysis to figure out which groups are significantly different, to then figure out which groups have higher and significantly lower scores. Also, for this example, I'm going to do it with an alpha level of 0.05 and 0.01 just to show you both ways to do it. In practice, you'll only have one alpha level given to you. Okay, so there's several pieces of information that you need to gear up to calculating the sum of squares, but they're relatively easy to find. So I'm going to go ahead and write down my formulas, our source table. We've got between, we've got within, and total. And the formula for total sum of squares is equal to the sum of x squared minus the sum of g squared divided by sample size for the entire study. And then within is just the sum of the sum of squares. And then between, I'm just going to do sum of squares total minus sum of squares within. Then we are going to have our degrees of freedom. And so degrees of freedom between is equal to k minus 1. Degrees of freedom within, n minus k. And degrees of freedom total, n minus 1. And then our mean squared, which is just equal to the sum of squares between divided by sum, degrees of freedom between, or for within, sum of squares within divided by degrees of freedom within, and then our F-statistic, which is just the mean squares between divided by the mean squares within. And I'm not writing those formulas down because by the time we get to this point, we'll already have everything that we need from the table. Okay, so if I'm looking at my formulas, I know that I need to find my sum of x squared. I need to find my g. I need to find my uppercase N. I need to, let's see, oh, no K. And I think that does it. And you know what? I'm also going to calculate my means for each group. So my means, I'll do that over here. And the mean is equal to the sum of t divided by n for each group. Okay, so let's go ahead and start with the means. So the mean for group 1, or let's go ahead and put group C for control group. Well, if we take 4 plus 1, we get 5. And we have 1, 2, 3, 4, 5 people. So 5 divided by 5 equals 1. If we find the mean for the fentanyl group, and I'm just finding these means because I want to look at the means to see how different they are, and I also want to have those when I calculate my Tukey's post hoc analysis if I find that these are significant. So the mean for the fentanyl group, so 6 plus 8 plus 5 plus 4 plus 2 gives me 25. 25 divided by 5 is 1. And the mean for my morphine group, so 6 plus 5 plus 9 plus 4 plus 6 is 30. And 30 divided by 5, there's 5 in that group, gives you 6 for those means. Again, I'm just calculating those in advance because I'm going to be using those for Tukey's post hoc analysis if I find significant differences. And I can look at this as a simple way to say, okay, well, so far, looks like morphine is resulting in the most relief. But let's go ahead and complete this to make sure. Oh, this should be 5. Sorry, guys. So now looking at this, looks like fentanyl and morphine are having about the same amount of relief compared to the control group, which is not so good. But we need to do a significance test to make sure that we would be confident that this result would pan out in the population. Okay, so I'm just going to write my means down here and 6. So the sum of x squared. So you have to square each x value and add it together. So I'm just going to kind of write the squared values next to all these to add it together. So 4 times 4, 16, 1, 36, 64, 25, 16, 4. 6 times 6 is 36, and 25, 81, 4 times 4 is 16, and then 36. If I add all those values together, so 16 plus 1 plus 36, all those values added together, you'll end up with 356. Now I need to find G. G, grand total. So 4 plus 1 plus 6 plus 8 plus 5 plus 4 plus 2 plus 6 plus 5 plus 9 plus 4 plus 6. Whew! So if you add all those together, and I'll start showing you those calculations. 0 plus 1 plus 0 plus 6, all the way. You end up with a G of 60. Now for sample size, you can simply just count how many participants are in the study. And I've already established that each group has 5 participants in it. So 5 times 3 groups, you get 15. And then K, how many different groups are there? Control, fentanyl, morphine, there's 3 groups. And remember, I found these so that I would have what I need to calculate my sum of squares values down here and my degrees of freedom values. So let's go ahead and start calculating the sum of squares total. So the sum of squares total is equal to the sum of x squared, which is 356, minus the sum of g, well, really just g squared, and g squared, so 60 squared, divided by 15. So this becomes 356 minus 3,600 divided by 15, which becomes 356 minus, well, 3,600 divided by 15 is 240. And you end up with a final value of 116 for the sum of squares total. Now, you don't have to show all of your calculations in the table. In fact, I strongly suggest that you do all the calculations above the table or somewhere else. Just make sure that your final answers are in the table. I'm just showing you this way so you'll have a nice, easy place when you go back and look at these notes to see everything that led up to what we got here. All right, sum of squares, those will be given to you. So just 12 plus 20 plus 14, 12 plus 20 plus 14, and you end up with a sum of squares within of 46. So we've got that value. Then to find sum of squares between, using the easy route, you take your sum of squares total, which we found to be 116, minus your sum of squares within, 46, and you end up with a sum of squares between of 70. All right. Moving on to degrees of freedom. We have 3 levels. 3 minus 1 is 2. That's our degrees of freedom between. N minus K, well, we found N to be 15. We've got 3 groups. 15 minus 3 is 12. That's our degrees of freedom within. And then moving on to mean squared. So for mean squared, I'm going to go ahead and do those calculations out here because I'm running out of room. So the mean squares between is just equal to the sum of squares between divided by degrees of freedom between. Well, the sum of squares between is 70. Degrees of freedom between is 2. 70 divided by 2 is 35. I'll just plop that right here. And then the mean squares within. So I'll draw a little arrow so you'll remember that that's what those calculations are for. So the sum of squares within divided by the degrees of freedom within. We found the sum of squares within to be 46. Degrees of freedom within is 12. And 46 divided by 12 gives you 3.833. And that is your mean squares within. 3.833. Then remember that your F statistic is your mean squares between divided by your mean squares within, or 35 divided by 3.833. Let me rewrite these. And 35 divided by 3.833 is 9.131. So that is your final value in step 3. That is your observed test statistic, your F value. Now, if you noticed, I started with step 3. And that's because I need to know my degrees of freedom between and my degrees of freedom within to find my critical value in step 2. So now that we're done with step 3, which is the calculation part of this, let's go ahead and do step 1, 2, and 4. And then find the effect size if it's significant. So step 1, stating the hypothesis. Now, this is quite different than before because, remember, if the ANOVA is significant, it's an omnibus test, so it just indicates whether or not there's significant differences between at least one pair of treatment conditions. But we don't know which ones. So when you think about how you are going to state your hypotheses, there's really only one way to do it. Because remember, ANOVAs aren't used for directional hypothesis. F is always going to be positive because it's computed from variances, which are always positive values, and extreme values will always fall in the extreme right end of the F distribution. So for this example, if we have 3 levels of this independent variable, then our alternative hypothesis will literally be written out as at least one drug group will have significantly different pain levels. Or pain relief. You could also just say at least one mu is significantly different. But it's always nice, in this case, to put your alternative hypothesis in terms of the actual study. Or you could say, at least one mu is significantly different. Writing it out is much easier than saying, mu1 doesn't equal mu2, or mu1 doesn't equal mu3, or mu2 doesn't equal mu3, or mu1 doesn't equal mu2, or mu3. Like, you just don't go through all that pain. Just write it out. And then the null is fairly simple. Mu1 equals mu2 equals mu3. If you had 4 groups, you'd have mu1 equals mu2 equals mu3 equals mu4. We're still using mu because we're still testing a hypothesis about the population. So what does the sample imply about the population if they received that drug? What would their mean be? Okay, step 2. We need to find F crit from the F distribution table. And remember, we are looking at an alpha level of 0.05 and 0.01. We're looking at the F table. You'll see degrees of freedom numerator, degrees of freedom denominator. Degrees of freedom numerator represents the numerator of the F statistic. And remember, the numerator of the F statistic, or the top of the fraction that you use to calculate F, is the between groups variance. So this represents degrees of freedom between, degrees of freedom denominator, the denominator of the F statistic within groups variance, degrees of freedom within. So remember, before, we found that our degrees of freedom between was 2 and our degrees of freedom within was 12. So degrees of freedom within, degrees of freedom denominator, 12. Degrees of freedom between, or degrees of freedom numerator, was 2. So 12, 2. So our alpha level for 0.05, the light face, is 3.88. And the alpha level for 0.01 is 6.93. So if the alpha level is 0.05, then the critical value was 3.88. Let me go ahead and write down here degrees of freedom between, or degrees of freedom numerator was equal to 2, and the degrees of freedom within, or the degrees of freedom denominator, or degrees of freedom error, as you'll see in the Q table, is equal to 12. So that's what we use to find this. All right, alpha level of 0.01, we found that critical value to be 6.93. So if we draw out our F distribution with 1 here, and let's go ahead and color code. Let's do alpha level 0.01 and then alpha level 0.05. So 3.88 and then 6.93. So to pass the test, to be significant with an alpha level of 0.01, we have to have an F value that's 6.93 or greater. With an alpha level of 0.05, we have to calculate an F that is 3.88 or greater to reject the null hypothesis. So we're expecting that there is some difference based on the drug that they receive, some difference in pain. Okay, so as you've probably already figured out, when we calculated our F statistic in step 3, it was 9.131. So I'm just going to rewrite that. 9.131. Let's color code you green. Where does that fall in this distribution? It's like way out here. It's a really, really, really large F value. So we're pretty confident that there is some group that is different from the other groups due to the independent variable or due to the drug. So in step 4, we can reject the HO. Hooray! And you can state that results suggest that there is a significant difference in pain relief. So significant difference in pain relief. That's what we were measuring. And that significant difference in pain relief is among those 3 pain medication conditions. Now at this point, we don't know which pain medication is significantly different from the others. And we don't know which one is, better or worse or any of that because we haven't done a post hoc analysis yet. But before we do the post hoc analysis, let's go ahead and look at the R squared, or the effect size. Okay, so for the effect size, you want to find eta squared. I'll put this here. So effect size so eta squared, which is the sum of squares between divided by the sum of squares total. And if you go back and look at the calculations that we already did, sum of squares between is 70, sum of squares total is 116. So we have 70 divided by 116. And you end up with an eta squared of 0.603. So this would be a very large effect. And we could say that 60.3% of all the differences in pain relief can be attributed to which group that participants were in. So this is all well and good, but we still don't know which groups are significantly different. So we need to calculate Tukey's HSD. So if you remember the formula for Tukey, we need to do this post hoc analysis. And again, the findings were significant. We have more than two groups. Got to do a post hoc analysis to really dig down into these results. So the honestly significant difference, according to Tukey, is equal to Q times the square root of the mean squares within divided by the sample size for one group. And again, this is going to tell you the difference necessary between two groups to be considered significant, or the minimum difference between two groups to be considered significantly different groups. So we need to find Q. And I know that the Q table is going to need the degrees of freedom error, which is equal to the degrees of freedom within, which we already established that the degrees of freedom within is 12. Well, I'm also going to need to know my alpha level, and in this case, I'm going to do it for both alpha levels. So alpha 0.05 or 0.01. In practice, you'll just have one single alpha level, and the alpha level that you use for the post hoc analysis should be the same alpha level that you used for the original hypothesis test. And then finally, for Q, we need to know K, and we've got 3 different groups. So let's go ahead and go to our table and find this value for Q. So we need to go down to the Q table. Keep on going. Okay. So degrees of freedom error is 12. We've got 3 different groups. So we're going to have a Q of 3.77 for alpha level of 0.05 and a Q of 5.05 for an alpha level of 0.01. So we're going to find 2 different Tukey's HSDs for the 2 different alpha levels based on Q of 3.77 or Q of 5.05. Okay, so for an alpha level of 0.05, we have HSD is equal to, remember, Q for alpha level of 0.05 was equal to 3.77. So 3.77 times, well, the mean squared within that we calculated earlier was equal to 3.83. 3.83. And the sample size for each group was 5. So 3.83 divided by 5. This becomes 3.77 times the square root. Well, 3.83 divided by 5 gives you 0.766. So this becomes 3.77 times the square root of 0.766, which is 0.8752. And you end up with a final value of Tukey's HSD for an alpha level of 0.05. That is 3.3. So 3.3 equals Tukey's HSD when alpha is 0.05. So in order to conclude there's a significant mean difference with an alpha level of 0.05, the difference between two means must be 3.3 or higher. Let's figure it out for alpha of 0.01. Remember, Q was equal to 5.05. So Tukey's HSD, 5.05. And we already know that the square root of the mean squared within divided by n is equal to 0.8752. So we just found that. So you do that math and you end up with 4.420. So 4.42, that is the minimum mean difference between two means necessary to conclude that there's a significant difference with an alpha level of 0.01. Okay, so now let's go ahead and figure out all of these mean differences to determine which groups are significantly different. So we have to take the mean for the control group minus the mean for the fentanyl group, the mean for the control group minus the mean for the morphine group, and the mean for the fentanyl group minus the mean for the morphine group. And I calculated the means earlier and I put those up here. So these are all the possible comparisons that you can have. Control fentanyl, control morphine, fentanyl, morphine. Okay, so the mean for control is 1, mean for fentanyl is 5, mean for control is 1, mean for morphine is 6, mean for fentanyl is 5, and the mean for morphine is 6. So 1 minus 5 gives you -4, but we really only care about the absolute value, just the absolute difference between the groups. So let's go ahead and put those little bars there to represent. We don't care if it's positive or negative, just the difference. So that's 4. 1 minus 6 would be -5, but the absolute value would just be 5. And then 5 minus 6, -1, but we just care that it's 1. So 4 is greater than 3.3, but 4 is less than 4.42. So the difference between the control group and the fentanyl group is significant with an alpha level of 0.05. So significant, but it's not significant with an alpha level of 0.01. So we could say, if we were thinking about, remember, p-values from lab, p is less than 0.05, but not less than 0.01. So there's less than a 5% chance that the difference between the control group and the fentanyl group is just due to random differences and not due to which drug was received. Okay, well 5 is greater than 3.3 and 4.2. So this one is significant at an alpha level of 0.01. Now it's also significant at a level of 0.05, but we automatically know if it falls in the extreme 1% of the distribution, if you're using, thinking about the distributions, or if, there's less than a 1% chance that the differences are just random and due to type 1 error, well then of course there's going to be less than a 5% chance. So we can just say significant alpha level of 0.05. So you know that the probability that the difference between the control group and the morphine group, the probability that that difference is just due to random chance is less than 0.01. Well, finally, 1 is less than both of these HSDs, 3.3 and 4.42, so it is just not a significant difference. So not significant difference. So you're going to have different conclusions depending on your alpha level. And typically in drug studies, we like an alpha level of 0.01. We want to be very cautious. We want to make sure that the probability of type 1 error is extremely low. Oh, so we need to change this to 0.01, sorry. So the conclusion differs based on your alpha level. In drug studies, we typically use the alpha level of 0.01. So if our alpha level was 0.01, the only one that we would find to be significant would be the difference between control and morphine. So our conclusion would be that taking morphine is better than taking nothing. But that there really isn't a difference between taking morphine and fentanyl or between taking fentanyl and nothing. So if our alpha level was 0.01, then our conclusion would be you want to take morphine. Fentanyl isn't that much better than a sugar pill, and morphine and fentanyl don't have a whole lot of a difference. Now, if your alpha level was 0.05, then both of these would be significant. And your conclusion would be that you would expect that in the population, either drug is expected to be equally effective for pain relief compared to no drugs at all. So let's go ahead and do one more example of all of the things that you'll do in an ANOVA. So let's say that law enforcement officials want to know the most effective way to stop repeat traffic violations. So they take 15 traffic offenders selected randomly assign 5 to 2 weeks community service, 5 to receive a $75 fine for offending a traffic violation, and 5 to 2 weeks of driver's education. And then they measure the number of traffic violations in the following year to see which ones were more effective. So we want to determine whether there's a significant difference in traffic violations depending on the program, the size of the effect if it's a significant finding, and which groups are significantly different if we find a significant ANOVA result. Because remember, the ANOVA just says there's a group different somewhere, but we don't know where. Alpha level in this case is just going to be 0.05. Okay, so I'm going to go ahead and write down my formulas that I'm going to be using. So, and then I'll put all the answers in a source table later. So this will mimic more what I want you guys to do when you show your work. It'll help you keep organized. So I'm going to start with my sum of squares total, which is equal to the sum of x squared minus g squared divided by n. And my sum of squares within, which is equal to the sum of squares. Then my sum of squares between, let's make this w a little more obvious, which is just equal to the sum of squares total minus the sum of squares between. I also need to find my degrees of freedom. We'll just stay in the same order. Degrees of freedom total, which is equal to n minus 1. My degrees of freedom within, which is equal to n minus k, and my degrees of freedom between, which is equal to k minus 1. Okay. Then my mean squared between is equal to sum of squares between divided by degrees of freedom between. My mean squares within is equal to sum of squares within divided by degrees of freedom within. And my F statistic is just equal to mean squares between divided by mean squares within. And I'm going to hope to put all these into a nice, neat source table. Now again, I'm starting with step 3 of the hypothesis test because I need to find degrees of freedom within and degrees of freedom between to find my critical value in step 2. Okay, so I'm looking at these formulas. I need to find x squared. All right, don't know what that is yet. I'm going to go ahead and find my means for each group as well, just to kind of have a preconceived notion of what I expect, and then I'll have those if I need them for my post hoc analysis. And then I'm going to need G. I see that here. Going to need N, uppercase N. Got my sum of squares already. Keep on going. Oh, got it in there. Oh, I need K. And I think that's it. That'll do. Okay, so x squared. So if we take 1 plus 9 plus 1 plus 16 plus 9 plus 36 plus 9 plus 16 plus 1 plus 4 plus 4, and these are just zeros, you end up with a sum of x squared that's equal to 106. And just to give you a frame of reference, it's 0 plus 1 plus 9, all those. Then to find g, the grand total, you just add all of the scores together. And so you have, 0 plus 1 plus 3 plus 1 plus 4 plus 3 plus 6, all those scores added together, and you end up with 30. So 0 plus 1 plus 3. Then n is just equal to the sample size for the entire study, which we already know is 15. That was in the description of the study. And you've got 5 people in this group, 5 people in this group, 5 people in this group. K, we've got 3 different groups. So now we're ready to plug in those values to find the sum of squares, degrees of freedom, mean squares, and F. So x squared, found that, it's 106, minus g squared, so 30 squared, divided by n, 15 people in the study. So this becomes 106 minus, well, 30 squared is 900, and 900 divided by 15, you end up with 106 minus 60. And 106 minus 60 gives you 46 for your sum of squares total. Then your sum of squares within, you simply add the sum of squares that were given to you. So 6 plus 6 plus 4. And 6 plus 6 plus 4 equals 16. That is your sum of squares within. Then your sum of squares between, you just take your sum of squares total of 46 minus your sum of squares within of 16, and you end up with 30. Sum of squares between. All right, now our degrees of freedom. Degrees of freedom total, so the total sample size for the study is 15 minus 1 is 14. That's your degrees of freedom total. Degrees of freedom within, 15 minus, we have 3 groups, 12 is your degrees of freedom within. And then we have 3 groups, k equals 3, 3 minus 1 is 2. That is our degrees of freedom between. Now I'm going to go ahead and start my source table here. So I've got my source, between, within, and then total. Got my sum of squares, my degrees of freedom, my mean squares, and my F value. Okay. So my sum of squares between was 30. Sum of squares within, 16. And hey, check it out. Add those together, and you get that sum of squares total that we found of 46. So my degrees of freedom between, I found that to be 2. Degrees of freedom within, found that to be 12. And degrees of freedom total of 14. And check it out. 2 plus 12 is equal to 14. So I'm feeling good. Now let's go ahead and figure out my mean squares between. So my mean squares between is equal to 30 divided by 2. And 30 divided by 2 gives you 15. So this is 15. And then my mean squared within is equal to the sum of squares within divided by my degrees of freedom within. So this is equal to 16 divided by 12. And 16 divided by 12 gives you 1.333. 1.333. And then my F is my mean squares between divided by my mean squares within. 15 divided by 1.333 is 11.253. That's huge. So 11.253. So there's a lot of calculations, but they're fairly straightforward, and it's so nice if you stay organized and then put your final answers into a source table. That keeps you organized when you have to go back and find pieces of this source table for the calculation of eta squared or for Tukey's HSD. Makes it easier for me to grade, and it just forces you to stay organized. Also, it's important to understand the source table because when we do this in Excel, you'll see something similar to this being produced as an output. Okay, so we're done with step 3. We know that F is 11.253. Now let's go ahead and jump into step 1. So for step 1, stating our hypothesis, we can just say at least one mu is significantly different. Or you can say, at least one group has a difference in traffic violations. But let's just keep it simple because this will always work. At least one mu is significantly different. Remember, we're putting it in terms of mu because we're using the sample to make an inference about the population. So that's our alternative hypothesis. Then our null is just mu1 is equal to mu2 is equal to mu3. So we would think that they'd all be about the same in the population according to the null. Well, step 2, we have to find F crit based on alpha level of 0.05, degrees of freedom numerator, I'm just going to abbreviate NUM, or the degrees of freedom between, which we found to be equal to 2, and the degrees of freedom denominator, or the degrees of freedom within, of 12. So let's go ahead and find F crit. Okay, so let's go up to the F table, find degrees of freedom denominator of 12, degrees of freedom numerator was 2, and our alpha level is 0.05, so 3.88 is our critical value. So 3.88. And if we draw this out, it looks a little something like this. 3.88. So any F value of 3.88 or higher is going to be considered significant. Well, we found our F to be 11.253, our F observed, 11.253. Well, that is way, way out there. It's very, very unlikely that we would see this result just due to random chance. So in step 4, can reject the null hypothesis, and results suggest that there is a significant difference in traffic violations depending on which program participants were assigned to. So results suggest there is a significant difference in the number of traffic violations based on the type of program that they received. Now, at this point, we do not know which groups are significantly different. And we don't even know what the effect size is. So we need to do 2 additional steps because we did find a significant result. So let's go ahead and figure out what proportion of the differences in traffic violations can be attributed to which program the participants were in. So effect size, eta squared. And remember, eta squared is equal to the sum of squares between divided by the sum of squares total. And when we calculated these before, sum of squares between was 30, sum of squares total was 46. So we have 30 divided by 46. And you end up with an eta squared of 0.652. So 65.2% of all the differences in traffic violations can be predicted by which program that participants were in. All right. Last step, we need to figure out which groups are significantly different. So in other words, we need to figure out Tukey's HSD and then compare that to all of the differences between each pair of groups. So HSD is equal to Q times the square root of the mean squares within divided by N. Well, we don't really know what Q is yet, but we know that our degrees of freedom error, or our degrees of freedom denominator, or degrees of freedom within, is equal to 12. We know we only care about an alpha level of 0.05 because that was the original alpha level for our hypothesis test, and we have 3 groups. So this is the same Q that we found earlier because we have the same type of information, or the same scenario with our degrees of freedom and K. But let's go ahead and find it anyway. It's good practice. All right, looking for Q. Alpha level of 0.05, just looking at the light phase type, we've got 3 different groups. And the degrees of freedom within, or degrees of freedom error, is 12. 3.77 is the Q that we're interested in. So we have our Q that we just found to be 3.77 multiplied by the mean squares within, which we found earlier to be 1.333, divided by N, and there's 5 people in each group. So when we do that calculation, we end up with 3.77 times the square root of 0.2666, which becomes 3.77 times, well, the square root of 0.2666 is equal to 0.5163, so 3.77 times 0.5163 of 1.946. So that is the minimum mean difference that's necessary between 2 groups for those 2 groups to be considered significantly different. So to be significantly different. Okay. That's an important number. So let's find all of the mean differences between every pair of groups that you can have. So the mean of community service minus the mean for $75 fine. The mean for community service minus the mean for driver's ed. And then the mean for the $75 fine minus the mean for driver's ed. So we have 1 minus 4. Remember, absolute values. We just care about the overall difference, not which one was higher or lower. We can infer that by looking at the means later. Community service, okay, so 1 minus 1. And then 4 minus 1. Well, we've got 3, 0, and 3. Well, these are both greater than 1.946. So we know that this is a significant difference with an alpha level of 0.05. So if we want to put this into plain English, then we can tell by looking at the mean. So the $75 fine had the most traffic violations, significantly more than community service and driver's ed. So in plain English, the $75 fine is significantly less effective than driver's ed and community service at preventing traffic violations. So see how now that we've done Tukey's post hoc analysis, we have really valuable information, whereas before we just knew that there was some difference somewhere. So I hope that this helped you understand the analysis of variance, and just keep in mind that it's appropriate to do the analysis of variance when you have two or more different groups that differ with respect to the level of the independent variable that they receive. You can do an ANOVA when you only have two groups, or you can do a t-independent samples test, but you cannot do a t-independent samples test when you have three or more different groups.